Comparative performance analysis of 60 and 80 SRAM cells by students of Vidyalankar Institute of Technology. These will be our subtopics for today. Let us start with abstract. In this project, we focused on comparing 60 and 80 SRAM cells. Both were designed using 180 nanometer technology of CMOS. Our main goal was to analyze how the additional transistors in 80 design affect stability, power, area, and speed. After layout simulations, we found that the 80 cell improved read static noise margin from 220 millivolt to 480 millivolt, which is a 118% improvement in stability. However, it came at a cost. The 80 design used 38% more area and was 22% slower in read access compared to 60 cells. So overall, the 80 design offers better stability and read reliability, while the 60 remains more efficient in area and speed. This comparison helps us understand the trade-offs that exist when optimizing SRAM for real-world applications. Let us start with the introduction. SRAM. It stands for Static Random Access Memory. It is widely used in high-speed digital systems because it offers low power consumption, fast access time, and compatibility with CMOS technology. But as CMOS technology is scaled down to smaller nodes, problems such as leakage current, reduced voltage margins, and instability begins to occur. The 60 SRAM cell has been the most commonly used design due to its high density and simple structure. However, it suffers from read instability, especially at lower voltages. On the other hand, 8 SRAM cells add two extra layers of transistors, forming a read buffer that isolates the storage node from bit line during reading. This improves the read stability and ensures that the stored data is not disturbed during read operations, which makes the 80 cell more reliable for low voltage operations. Literature survey. Previous research shows that CMOS technology scaling down can cause SRAM cells to face serious challenges such as leakage power, process variability, and decreased noise margin. One of the most important parameters in SRAM design is the static noise margin, or SNM, which measures the stability of the cell. Traditional 60 cells dominate due to their compactness, but many researchers have explored alternative designs, such as 7, 8, 9, or even 10T to improve reliability and power efficiency. Some also use assistive circuits that boost read and write stability at the cost of area. Based on this background, our study aims to provide a quantitative comparison between 60 and 80 SRAM cells to show which design is more suitable for future technology. For further discussions, I would like to call Arnav.
Methodology. In this project, both 60 and 80 SRAM cells were designed and simulated using Cadence Virtuoso based on the 180 nanometer CMOS technology. The process was carried out in a few stages. Schematic design, creating the transistor level circuit for both 60 and 80 cells. Layout design, converting the schematic into a physical layout while following the design rules. Post-layout extraction, to extract parasitic resistances and capacitances. Simulation using Spectre, for analyzing the cell performance such as SNM, delay and power consumption. Transistor sizes were carefully optimized for read and write stability. The area of the 60 cell was found to be 1.45 nanometer square while the 80 cell occupied about 2.0 micrometer square, mainly because of the additional read transistors. These steps helped us obtain accurate post-layout simulation results that reflect real-world performance. Circuit diagrams. Here we can see the circuit diagrams of both 60 and 80 SRAM cells. In the 60 design, there are 6 transistors, 2 two pull-up, two pull-down, and two access transistors connected to the bit lines. This configuration is compact and fast but can become unstable during read operations since the internal nodes are directly connected to the bit lines. In contrast, the 80 SRAM cells adds two additional transistors to form a read buffer. This buffer separates the read path from the storage nodes, which significantly improves read stability. Both designs were implemented in Cadence and their layouts were verified for DRC and LVS to ensure there were no design errors. These circuit and layout diagrams were the foundation for the performance analysis that follows. Now I would like Dhanush to continue for the further slides.
Results and discussions. Based on our simulation result, we analyzed the performance parameters of both cells. In old SNM, both 60 and 80 showed similar values, around 550 millivolt. In read SNM, the 60 cell had 220 millivolt, while this 80 improved it to 480 millivolt, showing a 118% improvement in reading stability. Read access time. The 60 had a fast read time of 90 picoseconds, while 80 took 110 picoseconds, making it 22% slower. In write time, both were similar, around 75 picoseconds. In dynamic read power, the 80 cell consumed 40% less dynamic power. And in static power, however, the 80 leakage was 47% higher due to the extra transistors. So overall, the 80 SRAM provides better stability and low read power, but at the cost of increased area and leakage power. So, in conclusion, our analysis that we conclude the 80 SRAM is more stable and has better read reliability, making it suitable for low voltage stability and critical application. The ST-RAM cell, on the other hand, remains more area efficient and faster, which makes it for ideal density focused design, like cache memory. Hence, the choice between ST and 80 depends on the target application, where the stability of density is main priority. This is a summary of ST versus 80 cell performance at 180 nanometer. So future scope, in future we plan to extend this work by performing Monte Carlo simulations to analyze the effect of process variations and exploring low voltage or sub-threshold operation for low ultra power systems and studying write assist techniques to further enhance performance as well as comparing array level performance and advanced CMOS nodes beyond 180 nanometer. Now, I would like to thank Department of Electronics and Computer Science at Vidyalanka Institute of Technology for providing us access to the lab resources and software tools. And we also like to thank Professor Akhil Masukar for his constant guidance and feedback.